Hello students, welcome all of you in online lecture series of microprocessors and microcontroller subject. In this lecture, we are going to study the interrupt structure of 8085. Today is our 8th lecture on M&M subject. My name is Pooja Subhashrao Deshmukh from International Center of Excellence in Engineering and Management College, Aurangabad. In last lecture, we have studied timing diagrams of 8085, in which we will see what are the important terms related to timing diagrams and what are the rules when we identify the number of machine cycles in an instructions. Then what is opcode fetch, what is read-write timing diagram for memory IO operation and memory read. Then what is memory write timing diagram, IO read, then IO write. These points we will cover in last lecture. So in this lecture we are going to study what are the types of interrupts in 8085, then hardware interrupt, in which there are two types. First one is maskable interrupt and second one is non-maskable interrupt. Then another one is software interrupt. So we will see one by one. The 8085 has multi-level interrupt system. It supports two type of interrupts, that is hardware and software. Hardware means what? Some of the pins of 8085 allow peripheral device to interrupt the main program for input and output operations. When an interrupt occurs, the 8085 complete the instruction it is currently executing and transfer the program control to a subroutine, that is services the peripheral device. Upon completion of the service routine, the CPU returns to the main program, and this type of interrupts in 8085 where CPU pins are used to receive interrupt requests are called hardware interrupts. The next one is software interrupt. In software interrupt, the cause of the interrupt is an execution of the instruction. Then these are special instructions supported by the microprocessor. After execution of this instruction, microprocessor complete the execution of the instruction it is currently executing and transfer the program control to the subroutine program. After that, upon completion of the execution, the subroutine program and program control returns to the main page. This is software interrupt, and the examples of software interrupts are DOS function, print string message, then exit, character input, printer output, etc. Here some interrupts are given. In interrupts there are two main parts, that is hardware interrupt and software interrupt. Again, hardware interrupt is divided into two types, that is maskable interrupt and non-maskable interrupt. This is the diagram of interrupt structure. The interrupt structure of 8085 has 5 hardwares, that is namely trap, that is TRAP, RST 7.5, RST 6.5, RST 5.5 and INTR. When any of these pins except INTR is active, then the internal control circuit of the 8085 produces a call to predetermined memory location. Then this memory location where the subroutine starts is referred as a vector location, or such interrupts are called as vectored interrupts. Then the INTR is not vectored interrupt. It receives the addresses of the subroutine from the external device. In types of interrupts, the 8085 except TRAP are maskable. When logic signal is applied to the maskable interrupts input, the 8085 is interrupted only if that the particular input is enabled. Then these interrupts can be enabled or disabled under program control. If disabled, 8085 disable the interrupt request, and the interrupt TRAP is non-maskable, which means what? It is non-maskable by program control. As you can see in the figure, the interrupt structure of 8085 indicate that the designed to respond edge triggering, level triggering or both triggering methods. Then we will see one by one. First one is TRAP instruction interrupt. This type of interrupts in 8085 microprocessor is non-maskable interrupts. Also, it is unaffected by any mask or interrupt enable. Means TRAP has the highest priority, and TRAP interrupt is edge and level triggered interrupt. This means the TRAP must go high and remain high until it is acknowledged. This avoids false triggering, which is caused by noise and transients also. As you can see in the figure, the positive edge of TRAP signal sets the D flip-flop. However, due to AND gate which is present in here, it is necessary to sustain high level on the TRAP input. Now there are two ways to clear the TRAP input. That is, first one is by resetting microprocessor, that is, it gives low signal on reset pin, and second one is by giving a high TRAP acknowledgement as a internal signal. By using these two ways, we can clear TRAP interrupt. The next one is RST 7.5. RST 7.5 is maskable interrupt. Then it has a second highest priority in the figure. As you can see, it is positive edge triggered, and positive edge triggered is stored internally by the D flip-flop until it is cleared by the software reset using the SIM instruction or by internally generated acknowledged signal. Then the positive edge signal on the reset 7.5 pin, it sets the D flip-flop. If the mask bit is M7.5 is 0 and that is RST 7.5 is unmasked, then the 8085 completes it. Also pushes the address of the next instruction onto the stack and load program counter with the fixed vector address, that is 00003CH. Due to that, 8085 starts execution of instructions from addresses 003H, which is starting address of an interrupt service routine of RST 7.5. This is overall about the RST 7.5. The next one is RST 6.5 and RST 5.5. Both are level triggered, and this type of interrupts in 8085 can be masked using SIM instruction. Then RST 6.5 has the third priority and RST 5.5 has the fourth priority. Also, the vector addresses for 6.5 and 5.5 are 0034H and 002CH respectively. After recognition of RST 6.5 and RST 5.5, 8085 completes its current instruction, which is pushes the address of next instruction on the stack and loads program counter with the corresponding vector address. The next one is the INTR interrupt. INTR interrupt is maskable interrupt but not the vector interrupt. Also, it has the lowest priority. Then there are some sequences for occur when INTR signal goes to high. First one is 8085 checking the status of the INTR signal during execution of each instruction. The next one is if INTR signal is at high, then the 8085 complete its current instruction and send an active low interrupt acknowledge signal INTA if the interrupt is enabled. Then after that, in response to INTA signal, external logic places an instruction opcode on the data bus. Then in case of multi-byte instruction, additional interrupt acknowledge machine generated by the 8085 to transfer the additional bytes into microprocessor. Then on receiving the instruction, 8085 save the address of the next instruction on stack and execute received instruction. This is all about INTR signal. Then next one is, this is the summary of all the interrupts, that is, first one is trap instruction interrupt. This is age and level triggered and the priority of this interrupt is first priority. It is not maskable and vector address is 0024H. Then second one is RST 7.5. This is age triggered interrupt and the priority is second. This is maskable interrupt and address 003H. Then next one is RST 6.5. This is level triggered interrupt and the third priority. Also it is maskable and address is 0034H. The next one is RST 5.5 interrupt. This is level triggered and the priority is fourth. This is also maskable interrupt and address to 002CH. Then last interrupt is INTR interrupt. This is also level triggered and the fifth lowest priority. It is also maskable interrupt and it does not having vector address. The next one is software interrupts in 8085. There are total 8 software interrupts which is present in 8085, that is from RST0 to RST7, means total are 8 interrupts. As you can see in the figure, whenever a software interrupt is generated, its vector address is calculated like this. Vector address is equals to interrupt number into 8. Suppose we have to calculate vector address of RST4, means RST4 is a interrupt number and we have to calculate for this vector address. It will be 4 is a interrupt number, 4 into 8 is equals to 32H, means 0020H will be the vector address of RST4. RST8085 having 8 software interrupts as told you, that is RST0 to RST7. The vector address for these interrupts can be calculated like the interrupt number into 8 is equals to your answer, that means vector address. The next one is maskable and non-maskable interrupts. As mentioned earlier, the maskable interrupts are enabled or disabled under program control. Then in this section, we will see how the interrupts can be masked or unmasked using program counter. There are four instructions which is used for control interrupts. That is, first one is EI, that is enable interrupt. Second one is DI interrupt, that is disable interrupt. And third one is RIM interrupt. And fourth one is SIM interrupt. Now we will see one by one in detail. First one is enable interrupt. The enable interrupt instruction sets the interrupt enable flip-flop As you can see in the figure, RST 7.5, 6.5 and 5.5 and INTR are enabled using EI instruction. Then it is important note that when any interrupt is acknowledged, interrupt enable flip-flop resets and disable all interrupts. To enable these interrupts in further process, it is necessary to execute enable interrupt instruction within the interrupt service routine. This is the function of enable interrupt. Next one is disable interrupt. Disable interrupt means the DI instruction resets the interrupt enable flip-flop, as you can see in the figure. It is disables RST 7.5, RST 6.5 and RST 5.5 and INTR interrupts. This is SIM. Then SIM is a set interrupt mask. This instruction is used to set the interrupt mask and to send serial output. Also, it transferred the contents of accumulator to interrupt logic and serial IO ports. It is necessary to load the appropriate contents in the accumulator before execution of SIM instruction. So you can see in the figure, SIM instruction, this is the SIM instruction format. Bit 0 is bit 0 to 2. It will be set or reset the mask bits for RST 5.5, 6.5, 7.5 of the interrupt mask register. Then bit 3 is used for enables the functioning of bits, that is 0 to 7. Means what? It enables or disables the masking control. Then bit number 4 is used to reset the RST 7.5 request regardless of whether or not RST 7.5 is masked. Then bit 5 is don't care. Then bit 6 is enable the serial output if this is set. Bit 7 is decides the data to be sent on the serial output pin of 8085. This is all about SIM interrupt mask. The next one is pending interrupts. Pending interrupts, in which we will see RIM, that is read interrupt mask. The read interrupt mask RIM instruction is load the status of the interrupt mask, then pending interrupt and contents of the serial input data line SID into the accumulator. Then it is possible to monitor the status of the interrupt mask, that is pending interrupts and serial input, the number of types in interrupts in 8085. When one interrupt is being serviced, the other interrupt requests may occur. If your requests are higher priority, 8085 branches program control to the requested interrupt service routines. But when the interrupt requests are of low priority, means 0 priority, 8085 store the information about these interrupts request. Such interrupts are called as pending interrupts. Then the status of the pending interrupts can be monitored using the RIM instruction format. You can see the figure of the RIM instruction format, in which bit 0 to 2 give the status of the interrupt mask, that is logic 1 indicate the interrupt is masked or not. Then bit 3 gives the status of the interrupt enable flag if 1 interrupt are enable, if 0 interrupt is not enable. Then bit 4 to 6 it gives the status of pending interrupt, and bit 7 is used to status of the serial input data line. Then last one is interrupt driven IO. You can see here the figure of the interrupt driven IO. When none of the key is pressed in all input lines are high and the output of the 8 input NAND gate is low. When none of the key is pressed, means there is nothing key is pressed, all input lines are high at logic 1 and the output of 8 input NAND gate is low, means 0. If any key is pressed, then the status of that line becomes 0 and the NAND gate output goes high, means at logic 1, which gives the interrupt signal to the 8085. Then the microprocessor execute the interrupt service routine to check whether which key is pressed or not. And then in this system, it is not necessary to microprocessor to check whether the key is pressed or not in between the program execution. But when key is pressed, interrupt is automatically generated and it initiates input-output data transfer. So it is referred as a interrupt driven input-output. This is all about interrupts. I hope everyone can understand this, but if anyone have doubt, you can contact me anytime. So, thank you very much.